Hello everyone, myself Dr. Sunny Kumar. I am an assistant professor in Department of Chemical Engineering, PKG College of Engineering and Technology, Panipat. Today I am teaching Chemical Engineering Thermodynamics 1. This is my lecture 9. In a previous lecture, we have discussed about energy balance for steady state flow process and related examples of it, and we have also did for the mass balance for steady state and the unsteady state, and we have also discussed the examples of mass balance also, and we have also solved some unsolved problem related to these balances, and and we have also discussed the pressure, volume and temperature behavior of pure substance, and and we have find what will be the critical points and the triple point in a PT diagram. This is not and this triple point and the fusion region and the line separated the region, and the liquid, gas, vapor, solid and solid liquid, where these phases are exist on a pressure temperature graph. We have discussed this. So if you will see, this is a energy equation which we have solved this is for the unsteady state flow process के लिए process, and when it will be time 0, so it will be, and the continuity equation, this is the continuity equation, and this is a general energy equation which have the kinetic energy. This one is the kinetic energy, this is a potential energy, and this is the internal energy. All energy are involved in this is a general energy equation. And then these are the heat capacity at a constant pressure, and we have so this thing and this one is heat capacity at a constant volume, which is related to the change in internal energy upon a change in temperature with respect to change in temperature. Okay, and then we will go for the pressure PVT behavior of pure substance, where we have discussed the pressure and temperature diagram, where we find some points like sublimation curve. So if you will see the sublimation terms, how sublimation comes that is a process when the solid directly comes to the gas, like when you burn this camphors, so they can directly changes into the gas, not in not comes the liquid. So that will be the sublimation point, you can say. So this is the sublimation curve we have discussed, and the fusion curve we have discussed. So you have seen how their liquid is changing to the different state, vapor to directly gases, say supercritical ones. So we have discussed that thing, and the critical point and the triple points. At triple points, at that points all three one exist: solid, liquid, gas. At this triple points, everything is exist. And why? And because you have also seen that the degree of freedom, if you will explain in terms of degree of freedom, so the degree of freedom for the triple point is we have also discussed, so we have solved. These are the things we discussed in the and the critical point when the vapor directly changes to the gases, so that is critical points. So this is a pressure temperature diagram which we have discussed in the previous class. So this is a pressure and this is a temperature. X-axis is temperature and y-axis is pressure. If you will see, this is a sublimation curve, 1 to 2 line, and 2 to C line is your vaporization curve, and this is 2 to 3 is fusion curve. So where the this is a solid region. If you will say, here in this area there is a solid region, here is a vapor region, and this is a liquid region. So these are the different states of your matter. So, and this is a fluid region, A to B, A is here to here, this is a fluid region, and this is a C point is the critical point. After that it comes to the gas region. So these are the things which is very important for this, and this is the critical temperature you are seeing here, and this is your critical pressure. So these are the terms we have discussed yesterday in the previous class. So today we will discuss the pressure volume diagram. So in the later one, in the previous one we have discussed the pressure versus temperature graph. Now we will discuss the pressure versus volume diagram and the PVT surface. Now the pressure, volume and temperature in one graph we will discuss. So that will be the 3D graph that explain our what will be the effect of pressure, volume and temperature when someone is changing. So you can directly find out at a specific point you can what will be the pressure, what will be the volume, what will be the temperature by this 3D graph. Okay, and next one is single phase region and the volume expansivity we will discuss also, and the isothermal compressibility. So these term also we will discuss. So this is your today topic. So now we will discuss about what is a PV diagram, which is the pressure volume diagram. If you will see here figure 3.1, so this is your figure 3.1. these are the two figures which are the 3.1 does not provide any information about the volume. So if actually previous the previous PT diagram that does not show any this volume information. So this is another figure. So it merely display the boundaries between the single phase region. So this is a PV diagram for pure substance showing solid, liquid, gas regions. So this PV diagram also shows the solid, liquid, gas region, showing liquid, solid, vapor and vapor region with isotherms. Okay, isotherms at a constant pressure. Okay, temperature, sorry. So on a PV diagram, this figure is 3.2a, and this is B. So these boundaries in turns becomes region where two phases, solid and liquid, and solid and vapor, and solid slash vapor, and the liquid slash vapor coexist in equilibrium. If you will see here, the curve that outline these two phases region represent a single phases that are in equilibrium. Their relative amounts determine the molar or specific volumes within the two phase regions. The triple point when we will do the this is a critical point, and at the triple point figure 3.1 in the last figure has becomes a triple line where the three phases with the different values of V coexist at a single temperature and pressure. Okay. Okay. So this is your figure 3.2a. If you will see here, this is a volume and here is a pressure. So when it is in a solid state and volume is constant, if you will see there is no change in a volume when you will compress your solid anything, because it is already solid, so there is no changes in volume. But so that means the volume will be constant for this. So this is a straight line here. And why this pressure is increased? Because when you are trying to some force on that force per unit area on a surface on a solid, so what will happen? There is no deformation is happen, but there is no volume change is happening. Due to this, you will get the same volume, but you are increasing the pressure. So this is your solid, but pressure is increasing, but volume is constant. So now in a solid, the liquid. So in case of liquids, there is slightly uh, volume can change. So this is your liquid line, the second one. Okay, and now this is your third line, which is a liquid versus vapor. So this is a when the volume is changing um, with the pressure. Initially it is increasing at a specific up to the critical point, and after that it is the pressure is decreasing and the volume is also decreasing. So this is the thing, the maximum you can changes in the volume here, and then after that it is going back. So this is your PV diagram. This is for vapor and this is for liquid and vapor can exist. Okay, and this is a C point is a critical point, and if you will see here, this is a solid dash liquid vapor line. Okay, here in this state solid and vapor can exist, and this is C, and this is a pretty critical pressure PC here, and here it is a TC, it will be the critical temperature, and here this will be the fluid, and this dotted line shows the gases behavior, and this line shows the vapor behavior, and this line shows the gas behavior. Okay, so these are the things when the when volume is changing and the pressure also changing. So this is the thing, this dotted line for gases, so and this black line shows for vapor. Okay, so next one, if you will see the another this at a different temperature volume, and here is pressure. So this if you will describe these two figures, these are the PV diagram for pure substance, where they are showing solid liquid gas region. Here they are showing solid liquid gas region, and showing liquid vapor and vapor region with isotherm. So this is your only for the liquid and vapors or gases, only liquid or vapor for this diagram. This is B diagram with isotherms. Here you are changing your temperature. So when the temperature is less than greater than critical point, so how the volume and pressure is changing, this is your dotted line, and when it is an critical temperature, so this is the behavior of pressure volume graph, and when it is a less than critical temperature, so T1, so it is the this is the dotted line which is in a vapor form. Here I think it will be the in gas form, and then this is when initially it is a liquid, and then liquid vapor phase JK, and then it is when the T2 is less than TC, very less than and the T2 is another temperature when which is less than the critical temperature. So this is another behavior you will see here, and the BC diagram when the pressure is changing but volume is very slightly changes in this case, but the pressure is very highly changes. So now, and then C to D, it is a very fast volume is changing at critical point, and the pressure is also changing, decreasing. So this is your two graphs which are showing the behavior of vapor and liquid and the solid when it is in the graph shows. Okay, so the figure 3.2 like figure 3.1, that is the PT diagram, represent the behavior of the vast majority of substance wherein transition from liquid to solid. Liquid to solid means freezing. So when the water is you will reduce the pressure, so what will happen, or when you decrease the temperature, so what will happen, it is a freezing, so it will become ice. So this is so liquid to solid freezing is accompanied by a decrease in a specific volume, increasing in density, and solid phase sinks in the liquid. Okay, here the reason water display unusual behavior in that freezing results in the increasing in specific volume, decreases in density. Okay, So you have seen when you will put ice on a water, so what will happen? They floats. They do not submerge, but they are floats because of and the density is decreases because so this is the reason. So figure uh, so this line suggests this one. So this is unusual behavior of water, but generally it is increasing other substance, but in case of water it is decreased. So and on figure 3.2, this is a 3.2 line labeled a solid liquid. Here are interchange of for water. Okay, ice therefore floats on liquid water, I have already told you. So where it is not so, the condition on earth's surface would be very vastly different. So the nature is nature, so we cannot change. So according to that we have to modify our laws. So this is another thing, very unusual behavior. Generally this shows at the molecular level. If you will see what will be the hydrogen oxygen contact angle and the bonding between the HOH. So this is a, and the angle between 109, I think. So that is changing, and surrounding whatever the arrangements of the water molecules that affects our density, the things. So this is the main. And in case of solid, what will the arrangements of the molecules, water molecules, that can affects our the density and the things at the molecular level. These are the things are changing. So figure 3.2 is an expanded view of the liquid and liquid vapor and the vapor region of the pressure volume diagram with 4 isotherms. So dotted line 1 2 3 4. So these are the 4 isotherms. These are different temperature, when the greater than critical temperature, and the when then or at critical temperature, when the less than critical temperature, and the very low temperature, less than critical temperature. So that these are the 4 diagrams which shows the behavior of the matter. So the with 4 isotherm path of constant temperature and superimposed. Okay, isotherms on figure 3.1 are vertically lines, and at temperature greater than Tc do not cross a phase boundary. So the on figure 3.2b, the isotherms labeled T greater than Tc is therefore smooth. So if you will see, this is a very smooth line. When it is higher than that critical temperature, it sometimes you can say it is for the gas. And the lines labels T1 and T2 are for subcritical temperature, and consist of 3 segments. So this is a one segment 1, and this is segment 2. The initial first segment, it is a liquid. The second segment, it can be the liquid or vapor, and the third segment, it is a vapor. So when in this these are the 2 lines which is called subcritical lines. Okay, and the horizontal segments of each isotherm represent all possible mixture of liquid vapor in equilibrium, ranging from 100% liquid at the left and 100% vapor at the right end. Here it is 100% liquid, and here it is 100% vapor. So this is the thing we generally observe, and here after that it is a vapor. So and in this condition, if you will see the temperature, there is no change in the temperature pressure, constant pressure, and in this dotted line is in constant pressure, only this line and this line, and this is at a subcritical temperature. So the locus of these end points is the dome shaped curve labeled BCD. This is a BCD curve, the left half of the which from B to C, here B to C, represents single phase liquid. This is a single phase liquid. At their vaporization boiling point, the temperature and the right half from C to D. So this is a right half, C to D. single phase vapor. Here it is a liquid phase and here it is a vapor phase at their condensation temperature. Okay, so the liquid and vapor represented by BCD. So this is a BCD. This is a liquid vapor representation by the BCD are said to be saturated, and coexisting phases are connected by the horizontal segments of the isotherms. Okay, and the saturation pressure is specific to the isotherm. Also called the vapor pressure. It is given by the point on figure 3.1. So in the figure 3.1 we have where an isotherm's vertical lines crosses the vaporization curve. So if you will see in a if you will see here, so this is a vaporization curve. Okay, we are talking about this one. So the liquid, the saturation phase isotherm, also called the vaporization curve. So we have seen where this exists. So the two phase liquid vapor region lies under dome BCD, under B, C and D. This is a D here. The subcooled region lies to the left of the saturated liquid base. So this is a saturated liquid curve here, B to C, and saturated superheated vapor region lies to the region saturated vapor curve, which is CD. So this is a saturated vapor region, and here is saturated liquid curve. Okay, this is for liquid and this is a vapor. So this is a saturated point region, and here it is a superheated vapor region. Okay, and like the left and right we have discussed. So the supercooled liquid exists at the temperature below and superheated vapor. So supercooled liquid exists at temperature below and superheated vapor at temperature above the boiling points for given pressure. Okay, so the isotherms in the supercooled regions are very steep because the liquid volume changes little. Okay, and the liquid volume change is very this is a super cool thing, I think, and this is very small changes in the volume and large changes in the pressure, but the change in the pressure is very high. The horizontal segments of the isotherm in the two-phase region. So this is a two-phase region. This is horizontal segments becomes progressively shorter at higher temperature. At high temperature, when the temperature is high, so this is very shorter. The two-phase region is doesn't exist here, but here it is a when the temperature is low, it is very high the phase region is high, but in the when the temperature is high, it is a very there is a very less segment to phase region. So high temperature being ultimate reduces to a point of critical point. So this is a critical point. Here there is a no existence of two phase region, very less, but here at critical point very small point of phase region, but after the less than the critical point the liquid vapor region exists. Thus the critical isotherms labeled Tc, so this is a critical isotherm Tc label exhibit a horizontal inflection at the critical point C. This is a critical point C, and at the top of the dome, so this is the top of the dome where the liquid and vapor phase becomes indistinguishable. So you cannot say what this is a liquid or vapor at this point. So we have discussed this pressure volume diagram. Once again I will discuss this in. Okay, so actually if you will see, this is a subcooled region. If you will see these lines, these are subcooled region, subcooled liquid, and here subcooled vapor here, and this is your critical point, and this horizontal line, these are some horizontal lines, and this is when the at a critical contamination. This is a two-phase region, which is liquid and vapor both exist at the less than the critical, and the two-phase region generally exist. And B to C is saturated liquid, and this is saturated vapor, and this is subcooled liquid and subcooled vapor here. Okay, and this is a we will say this is a two-phase region. Okay, so these are the two things. B to C is saturated liquid, C to D is saturated vapor. Okay, and when it is come from the top, this dotted line, it is a supercooled liquid, and this is two-phase region. After that, supercooled vapor. Okay, now we will discuss about actually superheated vapor. I will say super cooled vapor bola, I said supercooled vapor, but it is superheated vapor. So this dotted line here it is superheated, this is super heated vapor, and it is supercooled liquid here in this dotted line, and this is saturated vapor, liquid and saturated vapor. Okay, so now we will discuss about the pressure, volume, temperature, surface. For pure substance existing as a single phase, the phases rules tells us that the two state variables must be specified to determine the intensive state of the substance. So this is your PVT surface. This is a 3D diagram. This is volume, this is temperature, and this is pressure. When the pressure is changing from 100 to 0 to 100 bar, and this is temperature from 200 to 350. So the cooling range and the and boiling range. So this is the and temperature in Kelvin, and this is the volume is changing from 10 to the power minus 2 to 10 to the power 1 to 10 to the power 5. This is the for the different volume we are seeing here. So the for pure substance existing as a single phase, the phase rule tells us that two state variables must be specified to determine the intensive state of the substance. So this is the PVT surface for carbon dioxide with isotherm shown in black line. So these are the isotherms, these are the black lines, these some black lines, and the vapor liquid iso equilibrium curve in white. So whatever this is a white line, which is a vapor liquid isotherm liquid equilibrium curve in white line. Okay, so any two form amongst PVT, P, V and T can be selected as specified or independent variables, and the third can be regarded as a function of those two. Okay, so thus the relationship amongst pressure, volume and temperature for a pure substance can be represented as a surface in 3 dimensions. So you can say this in a 3 dimension you can represent. So you can also 3D diagram. So the PT and PV diagram like those illustrated in figure 3.1 and 3.2, and there is another 3.3 which I have not shown. So the slices of projection of the 3-dimensional PVT surface. So these diagrams are also included in this diagram. This is a slice projection of this. Okay, so now the figure 3.4 represents, so this is a figure 3.4 represent a view of pressure, volume, temperature, surface for carbon dioxide over a region including liquid, vapor and supercritical states. Isotherms are superimposed on this surface. The vapor liquid equilibrium curve is shown. This is because the white line. Vapor liquid equilibrium curve is shown in white with the vapor and liquid. Portion of it connected by the vertical segment. This is a vertical segment which is connected to this white line of the isotherm. Note that for ease of visualization, the molar volume is given on a logarithmic scale. So because the vapor volume at low pressure is several order of magnitude larger than the liquid volume. So in case of liquid, the volume change is very less, and but in case of vapor, the volume of at low pressure is very several order of magnitude, because the distance between the molecules are very large. So now the single phase region we will so this is your 3D diagram for we have discussed, PVT diagram we have discussed. So now we will discuss about the single phase region. For the region of the diagram where the single phase exists, there is a unique relation connecting pressure, volume and temperature. So express A analytically as function of P volume and temperature, which is equal to 0. Such a relation is known as PVT equation of state. So it relates pressure, molar or specific volume and temperature for pure homogeneous fluid at equilibrium. The simplest example, the equation for the ideal gas state, which is PV equal to RT, has an approximate validity for the low pressure gas region and is discussed in detail in the following sections. So an equation of state may be solved for any one of the three quantities pressure, volume or temperature, given values for other two. For example, if volume is considered as a function of temperature and pressure, then volume equal to volume is temperature and pressure, you can write. So you can write here like this: dV equal to dV upon dt plus dV upon dP. So this is a Taylor series expansion. You can write like this: dV upon dt and dt cancel in dP. So you can dV directly you can write like this, okay, which is constant pressure and this is constant temperature. So the partial derivatives in the equation have, so this is a partially derivatives, have definite physical meaning and are related to the two properties commonly tabulated for liquid and defined as follow. So the first one is volume expansivity. So when at a constant pressure, this is constant pressure, so when the constant pressure, so this term will be 0, only this term will remain. So you can write del V upon del T and 1 upon V, okay. So this is your volume expansivity. And the isotherm compressibility you can write, so K equal to -1 by V del V upon del P at constant temperature. So here is, and because it is a constant temperature, so this term will be Z. When you will integrate this one, so V comes here, so and the one constant also come here, so that will be the K, compressibility. Okay, here it can be the compressibility, the pressure, so it will be the volume. Okay, so the combining of these two equation, if you will combine these two equation here in the, you will put in this here, suppose it is a 3.2 equation, so then you will get, this is your final form of your equation, dV upon V equal to beta dt minus K dP. So this is your final expression you will get. So the isotherm for the liquid phases, I think this equation you are not visible to you. You can directly, so this is your equation. So this is your final form, dV upon V beta dt minus K dP. So the isotherm for the liquid phase on the left side, figure 3.2b, are very steep and closely spaced. So when there is no change in the very less change in the volume, very left in this left side. So thus both dV upon dt P and the dV upon dP T are small. So hence both beta and K are small in that case. This characteristic behavior of liquid outside the critical region and suggest an idealization commonly employed in fluid mechanics and known as incompressible fluid, and for which both beta and K are 0. For the incompressible fluid, we can say beta and K are 0. So the no real fluid is truly incompressible, but the idealization is useful because it provides a sufficiently realistic model of the liquid behavior for many practical purposes. No equation of state exists for an incompressible fluid because V is independent of temperature and pressure. So this is the thing, ln, if you will integrate that one, so ln dV2 upon V2, 1 to 2 state, so you can get beta T2 minus T1 minus K P2 minus P1. So this is a less restrictive approximation than the assumption of an incompressible fluid. So now we will discuss one example related to this single phase region. So if you know about the beta, volume expansivity, and this K, and the volume of the liquid acetone is at 20 degrees C and 1 bar is 1.287 centimeter cube gram inverse. So for acetone, find the value of del P upon del T V at 20 degrees centigrade and 1 bar, and the pressure after heating at constant volume from 20 degrees C and 1 bar at 30 degrees centigrade. The volume changes when the temperature and pressure go from 20 degrees centigrade and 1 bar to 1 degree centigrade and 10 bar. So this is I will give example, so you will do yourself. In this example we will discuss in the next lecture. So in the today lecture we have discussed about the pressure volume diagram and the PVT diagram, which is include the pressure volume and pressure and temperature diagram, and the single phase region we have also discussed. And in the single phase region, what are the things? Volume expansivity and isothermal compressibility, these terms are came, and we have discussed related to these. So this pressure volume diagram is very important for this some mass transfer operation like absorption or this especially the distillation column. You have required this pressure volume diagram. Okay, so for the different components, so this is very important. And the 3T diagram is represent how the three terms, the pressure, volume and temperature, is changing with respect to the individuals one. So this is the important. And the single phase region, so you have seen for when the is a subcooled region is there, so then the volume expansivity and isothermal compressibility, then the fluid behave as incompressible fluid. Okay, so this thing we have discussed in today's lecture. So in the next lecture we will solve the one questions which is I have given today, and you will solve in the next lecture. And the viral equations of state and the ideal gases we will discuss in the next lecture. And what are the different forms of the equation of states, we will discuss. What are the different scientists those are describe this thing, so we will discuss in the next lecture. So this is my email id chemicalsaniraj@gmail.com, and this is my website. If you want to contact me related to the thermodynamics or any other query related to this topic, so you can email me. And you can also, if you want to read something else, so you can this is my website, you can read here. So thank you very much for listening me.